We're now going to discuss vector functions representing two-dimensional lines in R2, which is the same thing as two-dimensional space. And we're going to start by remembering what it is to graph a line in two-dimensional space, basically using our algebra way. So this is 2x minus 1. We'll notice and remember that the y-intercept is -1 and the slope is +2. So we're going to go up to right 1, up to right 1, and we get another couple of ordered pairs that will enable us to graph this line. Now what we're going to do is express this line parametrically. And as you'll recall, in order to write an equation parametrically, essentially what we're going to want to do is let the x variable be equal to the value of the parameter. There are a lot of different ways to parameterize an equation, but one of the easiest ways is to let the independent variable be equal to t, and then the dependent variable y would be obtained by simply plugging t in for that independent variable here. And so we would end up then that y would have to be 2t minus 1 if we let our parameter be equal to t. We could let our x value be equal to 2t, and that would change what our corresponding y value would need to be. We could change our x value to being t squared, and then plug that in for our x, and that would change what our corresponding y value would be. So we could really parameterize this line in a lot of different ways. So let's determine the orientation of our line, essentially how that line is being traced out, by plotting some points based on this particular parameterization. So we can just run through some values of our parameter. So if t is equal to 0, I get the ordered pair where x is 0, because x is the same thing as t, and then y, we would plug 0 in for our t to determine the corresponding y value. Y is -1, and so we see that we are at this point when time is equal to 0, or the value of the parameter is equal to 0. It's a convenient way to discuss parameters to let them be equal to time, but the parameter does not always have to be equal to time. It's just a very nice tangible way to start our discussion. So if we let the value of the parameter tick through its domain, so now we'll let t equal to 1, let's see where we are on the graph as a result of that. So now we're going to plug in t is equal to 1 here, and I'm going to get my corresponding x coordinate is going to of course be 1, matching the t, and the y value is going to be 2 times 1 minus 1, which is 1. So we are here at time is equal to 1, or when the parameter is equal to 1. So we continue to move through the values of the parameter and create or determine ordered pairs so we can see where we are on the graph at that time. So when t is equal to 2, I'm going to be situated at the ordered pair where the x coordinate is 2 and the y coordinate is going to be 3. So here we are up here. So once we have some parametric values, then we can then see that the curve, or in this case line, is being traced out in this direction. And this is what we call the orientation of our line. Now in calculus, we're going to be expanding on this idea, and we're going to introduce the idea of a vector function, which essentially is a vector but that has an independent variable that is going to be this parameter value. And our vector function is going to be a vector written in, I'm going to say, pointy bracket notation, where we have an x component and a y component. We're in two-dimensional space here in this particular example. The x component of our vector function is going to be, in this case, we're creating a vector function for this two-dimensional line. So the parametric equations that we have chosen to trace out the line are going to be the components of my vector function. So we'll let the x component be this x parametric equation, and we'll let the y component be the y parametric equation, and this is what we're going to call the vector function for that two-dimensional line that we have just graphed. So now let's say that we have this as our vector function. we're saying that it's going to be tracing out this two-dimensional line. So let's think about it now as a table of values, but this time we're going to choose a value of the parameter and we're going to see what kind of a vector comes out of that. Notice that the input of this vector valued function is going to be a value of the parameter, and the output of the vector valued function is going to be a vector. So we input a value of the parameter and the output is going to be a corresponding vector. So let's see this play out a little bit. Again, we're going to let the value of the parameter start at 0. Same kind of idea as the table of values that we had a moment ago, but this time instead of getting an ordered pair as the output, we're going to have a vector as the output. So let's try this again. So we'll put in t is equal to 0, and the x component of our vector is going to be 0. The y component of our vector is going to be -1. Notice this looks just like the ordered pair that we had a moment ago, except for now we're using it as a vector. And then when we plug in t is equal to 1, we're going to get the x component as 1, and the y component is also going to be 1. Now, pointy brackets indicating this is a vector, not an ordered pair. And when t is equal to 2, our x component is 2 and our y component is 3. Another way that we can express this is to say that the vector value function, when we evaluated it at 0, turned out to be the vector 0, -1. When we plugged 1 into this vector function, we ended up with the vector 1, 1. And when we plugged 2 into the vector function, we ended up with the vector 2, 3. Again, the output of a vector function is going to be a vector. All right, let's graph these vectors on our Cartesian plane to see how in the world these might translate to that two-dimensional line graph that we saw a moment ago. So here we have 3 vectors. The vector 0, 1, if I were to write it where its initial point starts at the origin, its terminal point would be landing at these components, 0, -1. So 0, -1 is the terminal point of this vector, and we'll say that this is my vector valued function when we evaluated it at 0. So there's one of my vectors. My next vector is going to be the one that terminates at the ordered pair 1, 1. 1, 1 is up here, right? So the vector that terminates at 1, 1 and also initiates at the origin is this one here. So we'll say that this vector is the vector valued function evaluated at 1. 2, 3 is the terminal point of this third vector. So 2, 3 is going to be an ordered pair that's up here, and we'll see that I can graph this vector initiating at the origin and terminating at the ordered pair 2, 3. So these 3 terminal points are on the line that is that two-dimensional line we graphed a moment ago. And what we say here is that, or the idea is that, of course, let's go ahead and put that orientation in as well. So we see that at time is equal to 0, we were here. At time is equal to 1, we were here. Time is equal to 2, we were there. So we are tracing it out in that same direction. But the idea here is that the vector valued function r at t, which we have found to be t and 2t minus 1, is basically going to be a function that traces out the line with the tip or its terminal point. This function is going to terminate at points that are on the line, or we can think about that as tracing out the line with its terminal point.